Okay, so Physics 2820, Lecture 19. I want to deal with the three-body problem, or at least add another planet into our solar system and understand how the dynamics of multiple planets interacting in the solar system would work. So I'll review first what we covered last week, how we could write the equations of motion that follow from Kepler's law and Newton's law of motion and gravity, and how we could apply that to one planet and then extend it to two planets. So we have a planet-sun system. Okay, so here we go. The idea of this system of equations is the derivatives of velocity and position can be written in terms of their forces. And if you're dealing with Newton's gravitational law, that is the mass of the two objects times the universal gravitational constant g divided by the square of the distance between them, you get a traditional inverse square law. When you think about the vectors as components and split them into the right components, what that means is the x component is x divided by r cubed, and the y component is y divided by r cubed. So this is just taking the inverse square laws and casting them into the appropriate components, as we did on Thursday. This gives you a dynamical system, and one of the general themes of this course is many mechanical problems can be written as the derivatives of a bunch of variables is equal to a bunch of expressions. I'm calling this the right-hand side of the system of equations. Once you have the right-hand side, you can apply a numerical method to solve it. So what is that right-hand side? Well, the variables in this problem, there's an x, there's a y, there's a vx, and there's a vy. Together they form the state of the system, so I'm calling that the state. We only had one parameter on Thursday, which is the multiplication of g times m. It's never individually, so we can carry them around together. And the derivatives of x, y, vx, and vy are vx, vy, and then the right-hand side. The derivatives of x and the derivative of y are fairly straightforward. They're just the velocities. And the derivatives of velocities are accelerations, which is what the system of equations says. Once we define this system of equations, I can apply some numerical method. So I could apply something like a fourth-order Runge-Kutta method, but it could be an Euler method, or an implicit Euler method, or some other numerical scheme, something that's going to integrate the system of equations. The way that it works is it takes any right-hand side and evaluates its derivative, and then uses the numerical scheme to update the values of the state to figure it out for the next time forward. So this is one of the schemes we could use. We wrap this all together in some sort of application, a deriving program that's going to set the problem up and actually call the stepper to iterate through all of the different times and return the data. This is the classic pattern we've been doing. We initialize the state. We define any parameters we might need. We pass the right-hand side along with the initial state and parameters we want to use to solve it. And then we're going to use this pandas data frame idea to actually iterate through it to get the data back. So here's what you get when we solve it. It's returning back a series of columns, the x positions, the y positions, and the velocities in x and y along with the time. To visualize this, because of course a table isn't the easiest way of seeing the motion, we need some function that's going to visualize the different parts. So here's one idea. What we can do is we can have a function that plots the data x and y with a line. Maybe we'll do some other symbol for the sun, and we'll put right at the end of the position something for the time. We can make this interactive by having an optional parameter t max that says plot this data only up to whatever we're going to call the maximum t, which might be less than the total length of the simulation. The way that I'm doing that is I'm saying if you provide an optional argument t max, you actually give it something. If the t max is not none, then crop your data, basically slice it off, only consider the parts that are actually less than t max, and then do the rest. And so what that means is if you do an interactive plot with this data and let t max be something, the planet starts off at one location, and then what you can do is you can slide this forward, and you can see that what we're doing is we're having the planet trace out its orbit all the way around the sun. Now for this particular function, it takes two arguments. T max is the one that I want to vary. The data is fixed. I don't want to always recalculate the data. So what I can do is I can pass in an argument that says data has to be passed in, but I don't want you to produce a slider for it. I don't want to interact with the data. It's always going to be whatever data came out of the application. So it's a nice way of sort of viewing what the system is doing over time. And you can see that we've got an orbit of some planet around the sun. Now, I've set this particular problem up, so we're a distance of 1 astronomical unit away. So this is the Earth's orbit over 1 year. We can add in more planets just by running this simulation with different starting initial conditions. So if we start 3 planets all at the same distance from the sun, so the same 1 astronomical unit, you could pass in different initial speeds, and then for each one of these ones, we could do a loop and make a plot for all 3 of them. So this is a really simple function that takes a set of 3 different sets of data, and for each one of them calls planet plot. So what would that look like? What that means is you're going to see the 3 orbits, and with this slider, if you jump back to the beginning, you can see their behavior as a function of time. So the one that's traveling the slowest, it actually is at its aphelion, that is its furthest point away from the sun, and it has a highly elliptic orbit. The blue one, the Earth, has a circular orbit, and the green one, which starts off a lot faster than the other 2, also has an elliptic orbit, except for now, it's starting off at its perihelion, that is its nearest point to the sun all the way through. And as we saw before, things with larger orbits tend to have longer periods. It takes more time for that outer planet, the green one, to rotate all the way around the sun, even though the inner planet, that orange one, has actually done several orbits in the same amount of time period. Now, you could space these at different initial positions, and we could come up basically with a solar system. Okay, so let's do that. Let's extend this, so we're going to deal with multiple planets and actually space them out in some way. One of the tricks, though, with the real solar system is not only is there a force of gravity between the sun and each planet, the planets themselves have mass, and so there's a force of gravity between the sun and each one of the planets and between the planets themselves. The solar system is not a 2-body system. It's not the sun and the planet. It's actually a multiple body system, a many-bodied system of the sun and the Earth and Mercury and Venus and Jupiter and Saturn and all the asteroids and all the other matter which is in the solar system. Matter attracts other matter. That's what the force of gravity does. And it causes perturbations or changes in these orbits as they go around. Now, this change is not very large. It's predominantly elliptical, but it is measurable. And if you've had a chance over the weekend to watch the YouTube video that I recommended on the D2L site, this is by a YouTuber named Dr. Becky. She's talking about neat things about Mercury and the precession of the perihelion of Mercury. What that's really saying is the perihelion, that is the nearest point to the sun, itself is rotating all the way around. This ellipse is rotating as a shape all the way around the sun. When you looked at the precession of the perihelion of Uranus, what they could do is they could see that it was precessing, and they knew where some of the other planets were, like Jupiter and Saturn, and they could calculate what that precession was. But the precession wasn't matching what the observation of the precession of Uranus was observed to be. And so in 1846, this fellow named Leverrier said, well, one way of solving the problem is to add another planet which would perturb the orbit of Uranus just enough to make this work. And here's where that planet should be, and here's how big it should be, and what its period around the sun is. And so it was called the planet of Leverrier. And then a few years later, someone said, okay, let me look for it. They stuck a telescope up and they went, ha, there's Neptune. So go ahead and take a look at that video for part of that history. Continuing on with that history, though, is the precession of the perihelion of Mercury, which is due to the motion of Jupiter and the Earth and Venus. It's also do some neat effects in general relativity, and that's what that video is all about. So if we want to model this kind of system, we need to model the additional forces of gravity. Not only the force of gravity between the sun and the planet, but also the force of gravity between the different planets. Now, in general, the planets don't all have to lie in the same orbit. You can have a planet whose orbit is inclined relative to the orbits of the other planet, but we're not going to worry about that right now. We're going to assume all our planets are still in an XY plane, in one plane. You could extend it if you want to. Here's the equations of motion for a two-planet system. R1 is the position of planet 1 with respect to the sun. R2 is the position of planet 2 with respect to the sun. As before, there's a force of gravity between the sun, capital M, and planet 1. There's a force of gravity between the sun and planet 2. It's directed along the array, or the vector, from the sun to the planet. But there's another force. And the other force is the gravitational force between the two planets. Its gravity is dependent upon the mass of the first planet and the mass of the second planet. It depends upon how far away those two planets are. And so for the same reason as here, what it's divided by r squared and pointing along the vector that's between the two planets. Now, if you talk about the force of one planet on the other, by Newton's third law, that's going to be equal and opposite to the force of the other planet on the one. So you either could write these equations down as the vector from 1 to 2 with a minus sign here, or you can talk about the vector from 2 to 1, that is flipping it around, and just have one of these things being positive and one of these things being negative. The reason the signs are different is because these two vectors are the same. They're the vector from 1 to 2, the vector from 1 to 2 in all these different cases. And we've just used Newton's third law to flip them around. You notice that if you add the system together, that is, add these things together, these intra-system forces cancel out. So we only have left, if you want to consider the total gravity of the sun on the planets, these interplanetary forces all cancel out. Now, if we take these equations of motion, and we divide by the mass of m1, and we take the second one and we divide by the mass of m2, what we're left with is this system right here. It's saying what the position r1, the position of planet 1 is with respect to the sun, and including the force of gravity on the other. And one of the things you'll notice is the acceleration of planet 1 depends on its position, and it depends upon the mass of planet 2. The more massive planet 2 is, the more it's going to affect the orbit of planet 1. Likewise, the position of planet 2 is going to be affected by the mass of planet 1. So now mass 1 and mass 2 become parameters into this numerical model. So if you got the idea here of a sun and two planets, you got to sort of think of a triangle between the three. And so I don't know if this is neat, but I will try. Right. So what we got three objects. We've got a sun. Sun should be orange, and we've got a planet that's blue. And let's put a big Jupiter in there. Right. What we have between the two of them is you have a force of gravity on the Earth due to the sun, but you also have a force of gravity due to Jupiter on the Earth. The net force is the sum of those two things. In terms of these directions, these drawings, what we're dealing with is these three lines. The one on here is the distance from the sun to the Earth. This is the distance from the sun to, say, Jupiter. And this is the distance from Jupiter to the Earth. That's the R12. And that sets the three directions. So that's the triangle we're dealing with in this problem. If we're going to deal with two bodies that are moving, then you have to have twice as many variables. You need to have the coordinates for the first planet and the speed and the coordinates of the velocity of the first planet, and the coordinates for the second planet and the speed of the second planet. We're assuming that the sun is still so much more massive than these two things that we don't need to worry about it as well. But you could, if you wanted to have a third equation for the position of the sun relative to some origin, then you could add in a third term right here, and it would just be experiencing the force of each planet back on the sun. Remember, the force of gravity works two ways. Not only are you attracted by gravity to the planet Earth, strictly speaking, is attracted to you, your gravitational pull. It's just that the mass of the Earth is so big that it doesn't really respond very much, but it is there. The parameters GM, M2, and M1 are going to be given as parameters to this system. Okay, so let's try and implement this system. This is one of the things we need to be able to do. Given a set of equations of motion, can we write down this as a numerical model and solve it? Okay, so what we need is an equation or a function in Python that implements the right-hand side of this system. We need something that's going to return back those two things in their two dimensions, x and y, to give you the accelerations of the system. Now, these are vector quantities. So for when you see each one of these equations, it's an equation for x and an equation for y times 2. Okay, so what does that mean? What it means is if you take the coordinates, x1, y1, x2, y2, you can figure out what r1 is, as in the distance between the sun and the first planet or the sun and the second planet, by figuring out the square root of the first coordinate, or the square root of the first coordinate squared plus second coordinate squared. We're basically putting the sun at the origin and leaving it there. So to implement this, to begin to implement this thing, one thing that's going to be helpful is if we start by ignoring those terms. We take it and we say, yeah, it's there, but let's hold off. Let's leave those terms out. Get the problem to work with just two masses solved at the same time. Once we've debugged that and it's working, we can go back and we can put in this interplanetary force. But we don't want to throw it all out in the code at once because there are lots of places for errors, and this is a cleaner way of developing the code. Okay, so what would that mean? Well, I need to return back the derivative of x1, the derivative of y1, the derivative of the velocities, and then the same thing for particle 2 or planet 2. The derivatives of x and y are just the velocities, and the derivatives of the velocities are the accelerations given by the system of equation. And so in some ways, it's the same thing as we had before, but except for 4 equations, we actually now have 8 equations. That's the right-hand side of this system when it's been turned into a system of first-order equations. Once you have that system, we can write a driving application, something that brings it all together. It's going to be dependent on a lot more initial variables, the initial position, initial velocity of all the particles. We need a state vector, and we need to run through that. But we can use the same numerical method. There's more variables, which means you've got to define more things, and you've got to label more columns, because we've gone from 4 variables to 8 variables. In terms of setting this up, just for defaults, I put my first planet at a distance of 1 astronomical unit away. We know that if it's going to be a circular orbit, and this is something we talked about on Thursday, that the initial speed needs to be related to the square root of g times m divided by r. And in astronomical units, that is units of astronomical units cubed per year squared, g times m is numerically 4 times pi squared. So that means that I will get circular orbits if I take the initial distance from the planet to the sun, put that in this expression, square root of gm, 4 pi squared, divided by 1. I could put any default I want. I'm just putting in the sensible default, so I'll get a circular orbit. For planet 2, I can choose anything I like, but just for the purposes of a default, let's have that second planet be twice as far away. And for it to be circular, it needs to be the square root of gm divided by 2 all the way through. Why do I have square roots around the derivative? The derivative. So there's a question. Why do you have square brackets around the derivative? Oh, here. What I'm doing is I'm returning back a list of all of the different derivatives. So it's a list. It's like an array. The first value, second value, third value, fourth value. In Python, lists are defined by using square brackets with commas separating the elements. So I'm coming up with a list of items. I'm returning that back. It's a short form for a vector. Okay, so let's run that program and see if it works. Obviously, got to remember to run the code right there. So there we go. We've just got more variables. The first 4 have to do with the first planet. The second 4 have to do with the second planet. Because there are more variables, we can't use the same plotting routine as we had before. It was expecting only one variable. So one way to fix this is to use a plotting function, a new plotting function, that assumes you always will have 2 variables. Well, it's almost exactly the same, except for now I'm plotting the coordinates of number 1 and number 2. I need to have 1 sun, but 2 final positions. So here we go. This is what this should look like. Lo and behold, we are just solving for the system of equations for 2 planets at the same time. And once we get this to work and debug anything, then we can go back and make our system more complicated and add in the interplanetary forces. So in terms of a procedure, get the simplest version of a problem working and then extend it. So we've got the basics. These things are just going to have circular orbits. That seems to work, but there's no interaction between the 2. Let's add that interaction. The interaction is this term right here. The interaction, which we want to now include, is this guy right here. Right? I need the parameter M2 and M1 to be able to figure out the size of these terms. So this is something I'm going to have to pass into my function as a parameter. Okay, so here we go. I'm going to pass in not only the product of G times M, but also the mass of 1 and the mass of 2. I need to compute not only the length of the vector R1 and R2, but I also need the length of the vector R12. That is the distance between the 2 planets. I have the coordinates in X and in Y for the 2 planets. So if I just take their difference and then take the square root of that difference squared plus Y squared, this is the length of the vector. That's the distance between the 2 planets. This is what's going to define the strength of the other planets. We're just adding on more terms. For each planet, we had the acceleration due to the sun. And what we're doing is we're adding on the acceleration due to each planet. Now, it's a little bit different here from what you might expect. We said this was GM. I've written here GM times M2, and I've left this as a parameter. One might be a bit concerned and going, well, no, it should be like that. But I'll explain what I mean and why I've done that. If you remember in Thursday's lecture, we used units that are appropriate to the problem. We said for distance, don't use meters. Use the distance from the Earth to the sun and call that a standard unit called the astronomical unit. For time, what we did is we said, you know what, rather than dealing with seconds, how about we use years as a more natural unit for this problem? We're now bringing in mass. So what's the appropriate mass to use for the system? And when you're doing solar system modeling, the appropriate mass to use is the mass of your star. Everything should be relative to how massive the sun is. That's one way of non-dimensionalizing the mass units. And that's what we're going to do. Rather than having to deal with kilograms, let's report everything in solar masses. That is, the 2 masses are not so many kilograms. They're some multiple of the mass of the sun. Now, the sun is much more massive than each of the planets, so this multiple's a relatively small number. It's M1 is equal to the mass of the sun divided by 1,000. Or maybe you have a larger planet, which is 4% of the mass of the sun, right? These are different ways of reporting the mass, not in terms of kilograms, but relative to some other mass in the system. And this gives you a non-dimensional mass, a mass that I don't need to worry about how many 10 to the 27 kilograms this thing is. Relative to the sun, the first thing is 1,000th of its mass, and the second one is 4% of its mass. If we think about the expression G times M2, we can replace that M2 with M, or M2 times M divided by M. Basically, we're inserting a factor of M in this denominator and in this numerator, recognizing that G times M2 can be written as the mass in this non-dimensional unit times GM. G times M1 is this non-dimensional mass times GM. And that's what I've done up here. In this problem, M2 is not the mass in kilograms, it's the mass in solar masses as a fraction of the mass of how massive the star is. So we are able to pass in GM, the mass 1 and mass 2, where these are in non-dimensional units. There's lots of other ways of doing it. You don't have to use non-dimensional units, but this makes it very clear that these numbers are, this one's smaller than this one, and they're both much smaller than the sun. GM is a single variable. It's not G, it's G times M is the concept, but as a Python variable, it's one thing, and it has the value of 4 times pi squared in the units of astronomical units in years. Okay, so once we've got our system, and we do have to pay attention to the plus signs and the minus signs, and we should really think about whether or not this is implementing this system of equations. And so there might be some pen and paper work. You may need to write this out, expand it out, grab a piece of scrap paper, see if the equations that you have formulated are actually being implemented by this system. But once you've checked it, we can run this in some sort of solver. So again, we're going to pass in F2 planets into this routine. It's basically exactly the same code. I'm just adding in mass 1 and mass 2. That's the only difference in this code. And now I can take a look and see what happens. And I get an error because I probably didn't run that. Okay, here we go. So this is more interesting. So I'll start the simulation at T1. We're starting off with one planet at 1 astronomical unit away. The second planet is 2 astronomical units away. They begin to orbit. So far, nothing strange is going on. And the first planet, our planet Earth, happily goes around in a circle. It takes 1 calendar year to go. But you'll notice that after a year, it didn't end up in exactly the same location as it used to, right? Its orbit has been perturbed. Why? Because there's a gravitational force between this outer planet and this inner planet. So over the course of 2 years, what's happened is you've disturbed where our orbit actually ends up. Okay, so there's an interplay between the position of these 3 things causing this inner orbit to no longer be a nice, simple ellipse all the way through. So what's going on is an attractive force between these 2 things, so that's being pulled in this general direction. But it's more complicated than that because this object right here that's doing the pulling itself is moving around, and the strength of that pull is dependent upon how close this one is to this. So when these 2 objects are close together, there's a fairly strong pull between them. When they're further away, the pull between this planet and this planet is weaker. So now this is predominantly being influenced by the sun alone. So over time, there's a perturbation of the orbit of the inner planet. Now, there's also a perturbation of this planet as well. You can't see it because it's so much more massive than the inner one. We set this problem up so the mass of the Earth-like planet is 1,000th of the mass of the sun, and the sun is 4/100th, or the second planet is 40 times bigger. It's much more massive, still small compared to the sun, but much more massive. So it's being perturbed only very slightly, and this inner planet is being perturbed quite a lot. Now, real planets are not this massive, right? The mass of Jupiter is sort of this one right here, 1 divided by 1,000 times the mass of the sun. The Earth is much, much more smaller, think like 1/1,000,000th of the mass of the sun. Nor are the planets this close to each other, right? So I'm only saying they're 1 astronomical unit away. Jupiter is like 5 astronomical units away. We can simulate a more realistic solar system if we apply some data to it. So let's take up real planets. And we're going to talk about the precession of the perihelion of Mercury. Jupiter, which is the largest planet, is like in terms of millionths of masses of the sun, get about 1,000 millionths of the mass of the sun, 1 divided by 1,000 of the mass of the sun. But it's about 5 astronomical units away from the sun. Mercury, on the other hand, is a very small planet. It's only about 1/6 of a millionth of the mass of the sun. So these aren't in kilograms, these are in solar masses. And it's closer to the sun. It's only about a 1/2 astronomical unit, or 0.4 astronomical units away on average. The precession of the perihelion of Mercury is not nearly as dramatic as what I'm showing, but it's definitely measurable and can be observed. Now, what's actually precessing is the perihelion. That is the nearest point on the orbit to the sun. It's one way of talking about it. If you're going to talk about perihelions, you really need to be thinking about elliptical orbits. That is, orbits that aren't circles. Circles don't have a nearest point. If I just go and I consider any old object or any old sun, there's my sun, and I imagine some orbit going around this thing, which is circular, right? There's no nearest points. All points around this circle are basically the same distance. However, if you've got something like Mercury, which is a bit more, I'll exaggerate it, a bit more eccentric. Eccentric means more elliptical. Now, this is a massive exaggeration. You can see that in its orbit, the sun is at one of the foci of the ellipse. There's a time when the planet is closest to the sun. That's called the perihelion, near to the sun. Contrast that with the apohelion, all the way through the point when it's furthest from the sun. What precession means is this ellipse itself is rotating around in time, and we'll go through that. So when we're measuring the precession of the perihelion of Mercury, what we mean is this ellipse itself is rotating bit by bit. Now, I don't know if I can draw that really well, but I can try, right? So what we mean is we're doing, I don't have an ellipse tool that does it. The ellipse is doing one of these things. So as it moves around, it's precessing. And it's always elliptical, but the ellipse itself is rotating. This is highly exaggerated. Mercury does not precess that fast at all, but that's the idea. To talk about these elliptical orbits, when we're talking about an ellipse, we'll just give us a nice ellipse here. So here's a nice ellipse for us to work with. We typically talk about 2 numbers to describe an ellipse. We talk about this first thing, which is called the semi-major axis, and the second thing, which is the semi-minor axis. So often we call this semi-major axis, and this is the semi-minor axis. Now for a circle, these 2 axes are the same, so we just call it the radius. But for an ellipse, you have these different dimensions along the long side and the short side. One way of classifying an object as being more elliptical or more circular is to talk about its eccentricity. Eccentricity is a relationship between these 2 things. Notice that if B and A are the same, if B and A are the same, then 1 minus B over A squared is the square root of 0. The eccentricity is just 0. Circles have an eccentricity there. So how much eccentric are they? They're an eccentricness of 0. They're not eccentric at all. But in general, as the semi-major axis gets smaller or the semi-major axis gets larger, this number gets bigger than 1. And in general, for any ellipse you're going to draw, the ellipse can get more and more eccentric. And that just means that relative to its two axes, it's getting more stretched out. In the limit, as epsilon goes to 0, what you're basically, or goes to 1, you're basically talking about a infinitely thin ellipse relative to its width, straying into a line. Eccentricity can be defined for other conical shapes, but we're only going to focus for ellipses right now. So eccentricity is a way of describing how elliptical an orbit is. E is equal to 0 is circular, E is equal to 1, or approaching 1 is highly elliptic. You can relate the speed as something goes around the Earth to its location. We already saw this before in the previous setup. When I'm dealing with an orbit, right? So there's an orbit around something which might be circular. Then we said that if you're going to have a circular orbit, right, then what you need is the speed, v, to be equal to the square root of gm over r. We said that for a circular orbit, gm over r. If you have an elliptical orbit, the relationship is a little more complicated. For an elliptical orbit, for any point along here, the distance from the sun to your planet, you can call that r. You can figure out what the speed is at that location if you know that distance and how long the semi-major arc is. Now, this relationship is called the vis viva equation. Vis viva, Latin for living force equation. It's like historic. It's been around for a long, long time, pre-Newton. You can derive it by just conserving energy and momentum for the system. The Wikipedia page seemed to have a really clear derivation of it for those who like such things. But what it's doing is it's solving for the velocity as you go around here as a function for how long away you are. What it's also saying is as you approach the perihelion, the nearest point, it's going to speed up and it's going to slow down. So this is a relationship that lets us figure what the speed should be for any distance from the velocity to the sun all the way through. We can use this relationship cast in the language of eccentricity to model eccentric orbits. Okay, well, what is he talking about? Here we go. So here's just some geometry. If you got the sun, the eccentricity is the semi-major axis. You can talk about the distance away from the sun at perihelion, the distance away at aphelion. These are where the focuses are. If you know what this is the major axis, one of the effects of the eccentricity is the eccentricity, a number between 0 and 1, is the distance between the foci of the ellipse and the center of the ellipse. That's what E times A is. So this distance, the distance from the perihelion to the sun, is 1 minus E times A. That's how you can figure out this distance right here. If you go and you take a look at orbital parameters, if you look up what is the orbital parameters of Mercury or Earth or Jupiter, what you're going to find is described in terms of how long its semi-major axis is and what the eccentricity of the orbit is. Now, eccentricity is a number between 0 and 1. If it's 0, it's circular. If it's bigger than 0, it's elliptical. The Earth and the Jupiter are fairly circular orbits. These numbers are these eccentricities are close to 0. Mercury is a bit more eccentric. It's got an eccentricity of 0.2. But these are the numbers we can use to simulate real planets all the way through. Okay, so here we go. If I take this idea that I can, at the perihelion, rewrite that distance in terms of the eccentricity. So what am I doing here? I want this distance right here written in terms of the eccentricity. I have the vis viva equation, which comes from conservation of energy and conservation of momentum, that allows me to substitute it in. I can substitute in r equals this value to come up with this equation. So this is just doing the algebra. It says if you start an object at its perihelion with this particular starting velocity, you will achieve an orbit with the eccentricity that you want. That's basically how to think about this equation. It's a way of choosing the right starting velocity so that I get an eccentricity that I'm expecting. Okay, I'm going to do this thing not for just any generic two planets, but let's do it for Mercury and Jupiter. So the actual data, Mercury has a semi-major axis of 0.39, has an eccentricity of 0.207. Here's its initial position. Let's assume it starts off at the perihelion. Here's its initial speed. This is the speed required to have Mercury make an orbit with this eccentricity. For Jupiter, it starts off further away. It's not nearly as eccentric, but this is the speed needed for Jupiter to start off at that distance away. This is just defining some variables, and then we call that same two-planet app all the way through and take a look. Okay, so this is a map of Jupiter and Mercury going through time. And I'm just simulating a single calendar year. The orbit of Mercury is only like 88 days. It moves pretty quickly. Jupiter moves a lot slowly. So over a year of observing Mercury, it doesn't appear that Mercury is doing much at all. It looks like it's just tracing the same ellipse again and again and again. It's difficult to see what's happening to Mercury. Now, I could also plot not both planets together, but I could use my old planet plot routine. If I just relabel some variables, basically call data x equal to data x1, data y equal to data y1, I could just reuse that to zoom in on just this part right here. Yes, you could also change the limits or some other tool, but you can see that over the course of one calendar year, it doesn't really appear that the orbit of Jupiter is doing much at all. One way to see the difference is to pretend, for the sake of argument, that Jupiter is actually a lot more massive than it really is. If we run this same application, but set the mass of Jupiter in solar masses, not to be its original value, but to be 200 times bigger, a big Jupiter, then what you can see is, over the course of one calendar year, there's a bit of smearing in the orbit. This is the precession of Mercury. What we're doing is it started off that the near point between the Sun and Mercury started here, but over every orbit, what's happening is the near point is actually moving down right here. So if you think about these as ellipses, the ellipse itself is rotating in a clockwise direction everywhere around. So if you want to examine the amount of rotation or how fast that's rotating, we need to really figure out where these perihelions are. That is the near points to all these diagrams. We need to figure out when and where the near point is for each one of these orbits all the way through. If I can figure out where they are and when they occur, I can work out the rate of precession. Okay, so let's do that. Let's think about the distance from the position of Mercury to the Sun. I'm going to call that the variable r, which we've done before. I want to make a plot that shows where everything is. I'm going to plot the distance r as a function of time, the position x as a function of time, and the position y as a function of time. Okay, and then I've got some other stuff going on here. So you know what we're going to do? Let's do some commenting out, because I don't want to overthrow this diagram. We'll do this in pieces. Yeah, we'll do it like this. Okay, so here's the idea. We've got three lines. The green line is the y coordinate. The orange line is the x coordinate, and the blue line is the distance from the center. And you can see that this is in years, so approximately every 88 days, it comes back to the midpoint. But if we actually figure out where this perihelion is occurring. That is where there's a minimum, something interesting happens. Now, I got to find a way of figuring out where that perihelion occurs. Well, the perihelion is going to start off at 0, okay? We've created the problem so it starts off at 0. What I can do is I can look for points. I can loop through here and check whenever, at any point, whenever the radius to the left or to the right is bigger than the current radius or the current distance away. If that's true, I'm going to call that where the perihelion is occurring. So what I'm doing is I'm taking my data. I have a loop. I'm looping through everything. And I'm looking for the points where, for this given point, the time above and the time below, or the time before and the time behind, are each further away than I am from the sun. If I'm in that situation, I found the perihelion. So what that means is I can identify these solid lines. This is where the perihelion, or when the perihelion is occurring. Once I know those positions, what I can do is I could identify where the perihelion is occurring. So there's two things here. It's when there's a perihelion and where there's a perihelion. This is searching all the way through here in time, trying to find the point at which the distance from the Mercury to the sun is at its minimum. And then when it's found it, it's drawing a line there for a visual reference. But if I know what index that's occurring, I could also go and plot dots where this line is crossing all the way through. So I'm going to do that now. I'm going to add some dots to show you where the perihelion is occurring. So where, in the sense of this minimum point starts here, but over time, it's slowly moving around the circle. The ellipse is precessing. What that means is the location in X and Y coordinates of where the perihelion is moving around. You can see that in this plot because these dots, which represent X and Y coordinates, it starts off where the perihelion occurs at the Y coordinate of 0. But can you see how these black dots are slightly moving below the line? What they're doing is the perihelion is no longer occurring at Y equals 0. It's occurring at Y a little bit less than 0, a little bit more negative. And it's hard to see, but if you zoom into these pictures, this orange curve relative to the blue curve are getting a little bit out of sync. The orange curve is moving a little bit faster than the blue curve. The X is not occurring all the way to the right. It's moving a little bit more to the left. What's going on is the perihelion is shifting around this circle. Well, I could record those numbers. I could go through and I could say, okay, I found this pair of dots, this pair of dots, this pair of dots, this pair of dots, and so on. So let's do that. Let's create a dictionary structure like we've done before, recording what the time and position is of the perihelion. And then every time we found one, let's make a record of that one again. So what this is doing is it's an algorithm for figuring out where the perihelion is. Now, I've done it in this way of lists and dictionaries so that I can quickly turn this into a pandas dictionary, a pandas data frame, and then I can do manipulations like taking arctangent on the y coordinate and the x coordinate to figure out the angle of it. So in terms of data, you can think of the perihelion being at an angle of 0 and then moving through and rotating in a clockwise direction. That is, it's moving from here down, down, and down. I can take my planetary orbit, and for every one of the rows in this dictionary, or in this pandas table, I can plot a line that goes from the center off to that coordinate x and y. Now, it's a little bit fuzzy. It's not exactly a perfect algorithm, but it generally is showing the trend that the precession of the perihelion is moving in a clockwise direction. If I was to plot this angle as a function of time, so I'm plotting the angle as a function of time, you can see that there's a general downward trend. As time goes forward, the location of the perihelion is decreasing. Now, There's some noise in this algorithm, there's some error, but there's a general linear trend. If I want to understand the rate, one way of estimating the rate is to do a best line fit through it all. That gives me the average rate of change of the angle of the perihelion with respect to time. And what I'm finding is for a 200 solar mass or 200 times more massive planet of Jupiter, it will cause a 0.1 radian per year change in the orbit, right? Now this sequence of steps, so I've gone and drawn these sequence of steps out by drawing 1 plot, 2 plots, 3 plots, 4 plots to explain the algorithm, to try and check how the parts work, and to debug it when it wasn't working. I could take all of the logic in these 4 cells, so solving the problem, figuring out where these perihelion points are, constructing this best fit, and calculating whatever that slope is, and I could bring that all into a single function. So I'm going to call this estimate precision rate. So the idea here is this does all the logic, but none of the plotting. So in one go, you can just pass in a certain multiple of the mass of Jupiter, a scaling factor S, and get back out what the rate of precession is. Now, ideally, we could just put a scaling factor of 1 into this thing, and that would give us the precession of Mercury due to Jupiter. And if I do that, I get a number. However, if you go back and you look at these plots and you do it for 1, you're going to find out that the noise, basically these little errors, are so large that I don't find this result very convincing. There's enough error in this algorithm for finding the location of the perihelion that I'm not sure we can trust this number very much. However, if we're relatively confident with the rate of precision when the mass is at 200, what I could do is I could run this analysis for several different masses and come up with the trend of how this rate of precision depends upon the mass of our big Jupiter. And this is another thing we sometimes do. We do parameter searches. So what I could do is I could run this program many times, having the mass change from like no mass at all up to a mass of 200 times. And every time I go through the loop, do that algorithm to calculate the rate of precession. There we go, and plot it all together. As I said, the individual method seems to have some error. There's obviously something I'm missing in the construction. It's not a perfect precision, but there's a trend. And the trend is as you go from a very massive Jupiter in terms of a scale factor, and you shrink it towards 0, the rate of precession gets smaller and smaller. So there is some error in this algorithm. I don't have it all lined up on a nice little dot. There's other stuff going on, but there's a general trend that at least to first order, the amount of precession of this perihelion depends upon the scaling factor. So what I can do is I can take this scaling factor and substitute in a scaling factor of 1 to come up with an estimate for what the precession of the perihelion of Mercury is. Okay, so here is an approach where we've taken the system and we've estimated how much the perihelion of Mercury is precessing around as due to the gravity associated with Jupiter. Now, it's pretty small. It's only like 1/100th of a radian per year. And if you did watch that YouTube video, you'd find out that you need to be talking about, they typically talk about so many hundreds of arc seconds per century, right? So it's a slow precision. The precision of Mercury depends upon other planets. Jupiter is one of them, but Venus, I think, is the strongest. And the Earth also caused an effect to it. What we're looking at is the initial state, assuming these two planets started off aligned with each other. There's a little bit of perturbation of the orbit, and we've got to average this out. So this particular algorithm would require a little bit more work before I'd be confident for saying that this actually is the precession of the perihelion of Mercury due to Jupiter, but that's the general idea. You could do this for several planets. You could add them all up together and come up with the precession of the perihelion of Jupiter. So what I'm showing here is primarily, here's the takeaway. Here is an example where we've gone from a 2-body problem to a 3-body problem. We've illustrated how to take a second object and add it into the mix so that you have interplanetary forces, and showed how you can solve that kind of problem to answer some question about it. Okay, so we could continue this. I have a couple other places I could go with this topic, but I'll do it this way. Okay, so this idea, this concept of taking interparticle or interplanetary forces and modeling what's going to happen. I've got our last assignment prepared. It's only one question. I didn't want to give you 2 questions. I don't have it due until the middle of next week. So you have over a full week. And what I want you to do is look at a 3-body problem where this is the potential. Now, we're going to talk in the lab about how potential and forces are together. So this particle right here is sort of like the 3-body problem. It's similar, except for now what we have is 3 masses. All masses are closer. It's a mass of 1, 20, and 2. All 3 masses are going to be moving relative to each other. So you have to set up a coordinate system. The coordinates of those 3 masses are as given, and they have some initial velocities. Unlike the solar system, where we assume the sun is so massive it's not really moving, in this problem, you've got 3 particles with 3 equations of motion. You're going to have 12 variables in this problem. You're just going to extend what we've done to the 3-variable case. The force between them is not the force of gravity. It's a thing called a Leonard-Jones potential. When you're doing molecular dynamics, you want to include the fact that 2 molecules will be attracted by, say, van der Waals forces. So in general, we're dealing with molecular things. There's a net attractive force of 2 molecules together. Now, if their molecules are far away, it's very, very weak. As they get closer, this attractive force gets stronger. But it doesn't go on forever. Unlike gravity, which will pull things together until they smash in together, molecules, though they might be attracted by van der Waals forces, if they start to get so close that their electron clouds are pushed away from each other, you're going to get actually repulsion. 2 molecules will get attracted together unless, say, they're so tight or so close, at which point they'll be pushed away. That behavior can be modeled by an expression called the Leonard-Jones potential, where potential, as in the energy associated with the potential energy of the interaction, can give you the force by taking the negative derivative of that position. Now, I want you to solve this problem for the assignment, but it's not due for a week, and that's partly because I want you to do the lab first. I've got a lab which is going to go and talk about some of these ideas to give you the tools you need to be able to complete this assignment question. But this is an example of molecular dynamics. We're going to look at a 3-body problem and solve it. The lab is just the gravitational problem. It's the same thing we've been doing with respect to the planets, except for I'm going to start the problem from the gravitational potential of gravity. Gravity, this minus g m1 m2 divided by r squared thing, is a conservative force. It's a conservative force, so we can write down a potential function. A potential function is a function that when you take the negative derivative of the potential, you get the force back. It's one of the properties of conservative forces. For 2 masses, m1 and m2, the potential is minus 1 over r. Taking the derivative of that with respect to r gives you the 1 over r squared. And then if you take the negative of that, you get the negative 1 over r squared relationship for an attractive force. Okay. Ignore the details of the GM. We're just going to set the G and M, or the G, to be 1 in this problem. Everything's non-dimensional. The numbers are all without units. Don't worry about units. Assume the units are chosen so that we can just choose these numbers. What I want you to do in this lab is I want you to set this problem up. Now, if r is the distance between 2 particles, and the particles are defined as being in coordinates x1 and x2, and y1 and x1 and y1 and x2 and y2, we want to be able to write down this potential in terms of those coordinates. So this is something with SymPy, which we've tried to do a little bit more. So here's a bit more of it. The idea is you can use SymPy to calculate this expression. So what I'm getting at is, what is a SymPy expression? They would implement this in terms of x1, y1, x2, and y2. So it's a SymPy expression, which means it's going to be somewhere in here. There's going to be an SP dot square root, a SymPy square root of something, and you're going to want to put the minus sign out in front, and you've got to figure out what goes in the middle. Well, what goes in the middle is whatever R is, right? Oh, sorry. Whoa. Let's try this again. 1 divided by R. R is the square root of something, right? It's the distance between two particles. U is going to be minus 1 over the square root of whatever that is. Once you have a potential, you can figure out the force on it by differentiating. Now, in general, these forces are vectors. The forces could be in the x direction or the y direction. We talk about the potential in terms of R, but in general, the potential is actually a function of x and y. So to figure out the forces, we differentiate with respect to x. This will give us a SymPy expression. We can turn that into a NumPy function by calling lambda phi. So you're going to work through this thing. Come up with an equivalent function for y as well. Once we've got a function that describing the pull, as in the force of gravity on particle 1 due to particle 2, you can solve for the motion of this system. Well, in this problem, what I want you to do is assume the system is set up so you have two particles that start off at these coordinates. They're starting relatively far away. We're not dealing with astronomical units, but it's sort of similar. They're very far away. One is at the coordinates minus 10, minus 1, and the other one is at 10, comma 1. They're moving towards each other. At some point, they're going to start to feel this attractive gravity-like force. I want you to fill in the equations of motion, the starting values all the way through. Read the question. Define a state vector to initialize the system, and then try and figure out, and this is really where the work of the lab is, what the appropriate right-hand side equations are. What is the equations of motion for the system? I encourage you to use some scrap paper, write down what the equations are for particle 1 and the equations are for particle 2. It's all going to be in terms of these force functions. x1 and x2 are the positions. And one of the things I'll give you as a big hint is, remember Newton's third law. The force of particle 1 on particle 2 is the negative of the force of particle 2 and the force of particle 1. As soon as you have the force of one thing on the other, you automatically have the force of the second particle on the first. Just take its minus, the negative of that. Remember, these masses are not going to be the same. Solve that problem and make a plot. And then I've got a few little questions for you about which particle gets deflected more, and I want you to think about energy and answer a question. This lab follows very directly in terms of what we've just done in the lecture. So I'm around, Kyle's around. Hit me up on Zoom, share your screen, use your mic, talk to me. I'm here, as is Kyle, to help you out with this lab. So we have an assignment which you're going to work on after working on the lab, and then you are done the work of the course. Okay, the course. Got some comments. Okay, so, nope, wrong button, sorry.